Hello, everyone, and welcome to this talk. This is Then We Shall Code in the Shade, Creating Shaders in Unity. I'm Oh, geez, I'm talking to myself. Don't worry about that. I've just closed the YouTube tab. But it's a good thing to know that my audio is working. So, yeah, today we're going to look at creating shaders in Unity. I've done a similar talk to this in previous times. So if you want to have a look at that after this, it might be a very useful resource for you. I'm quite pleased to be able to start off Enhancement Week. Enhancement Week's such a great experience, and I thoroughly enjoy all the talks we have. And I'd also encourage you to go to as many as you possibly can, because it's just such a good experience. If you have any questions throughout this, if you feel like I haven't explained something very well, or I've gone off on a bit of a tangent or something like that, feel free to just drop a comment in the chat, and I should be able to field your questions, elaborate and help you out. So yeah, let's get into it. So today's session, we're gonna do two real things here. We're gonna mostly focus on the talk. So we're gonna go over a bit of primer for shaders. So the idea of this talk is that you can have some knowledge of shaders and computer graphics in general, but it's not necessarily required. If you don't know anything about computer graphics, that's fine. We're going to cover kind of the basics of that, so you should be able to follow along with this talk. Okay, I guess. Then if we have time, we're gonna have just a quick break. I don't know, maybe 1 minute, 2 minute. I might show you some resources on shaders or something like that, but largely it's just an excuse for me to kind of catch my breath and have a drink of water. I don't know why my voice, my throat, I was just talking to Kieran about this. My throat gets very dry when I give these talks. I don't know why, so I've got a trusty bottle of water here. And after that, we're going to go into the practical demo. So I'm going to open up Unity, show you how to build these shaders in Shader Graph. And you've probably heard, if you're interested in shaders and you've done some Unity, you've probably come across the terms Shader Graph. So we're going to walk through that, and I'll show you a bit about it. But the most useful part, the meat of this talk, is to do with the actual shader primer and this kind of stuff. If you want to learn more about the how to create specific effects, that's what my previous talk did, which you should find on if you're watching this on YouTube, you should find it on this YouTube channel. There we go. And just a disclaimer as well. So at the end of this, you won't, you're not going to be a shader guru, so to speak. You're not going to be an absolute wizard with shaders and you'll be able to create all kinds of effects. The idea of this is just to give you enough to get started with writing shaders, and to point you in the right direction of some tools that you can use to create them. Okay, so hopefully this is a useful talk. If you have any questions, like I said, I implore you to ask away. I'll be more than happy to answer any questions you have. So a bit about me, and I apologize about this photo. This is the only one I could find on my desktop. And I thought it was quite funny, actually, because it's looking at the about me text. I don't know. Anyways, so a bit about me. I love making games. I've been here in the university for a while. I work as a senior games developer in a company called Pixelica, and I specifically have an interest in anything relating to computer graphics or visual effects. On top of that, I love VR. Anything to do with VR or AR, I absolutely love, and that's what I'm currently doing my PhD in. I'm looking into motion simulation in virtual reality and how it affects the way people play games. And I'm also a senior software developer here in the School of Computer Science. So I work on some software-related projects, and I also help out my my colleague Ollie, who is sat next to me and waving at me. So yeah, but yeah, I do some software development for the school. The screens that you might have seen if you've been going around campus, not the campus, sorry, if you've been going around the first floor in IMB or the second floor, you might have seen those displays that have gone up. Well, That's something that I made recently. But I just want to give you an idea of kind of where I fit in the school. You've probably seen me walking around or seen another talk I've done, or, you know, you've most likely seen me making tea on the first floor because that's seemingly all I ever do. But yeah, but that's me. But let's get into this talk. So the first question you might have, I guess, is why? Why would you ever bother being concerned with writing shaders and making shaders for visual effects? Well, there's a couple of good reasons, and here are just some of them. The first, and one of my favorites, is the fact that you're not limited to pre-made assets by other people. You can create the visual effects that you specifically want, and because of that, you can create games, you can create experiences that look exactly the way you want them to be. Okay, so you're not limited to, you know, downloading a similar kind of thing on the asset store and tweaking it to make it look like something you want. You can just go and build the shader that you want, create the visual effects that you want, and for that reason, it can give you quite a lot of freedom in creating, you know, parts of your game. You can create really cool in-game effects that can take your game from something that, you know, looks a bit game jammy, you know, made it in a couple of hours, to something that looks and could compete with some of the games you see on Steam, you know, some of the AAA games or some indie game. Visual effects can really do that. You know, they can take a game from something that's kind of rough around the edges to something that's really polished and is a good end product. Another reason is it's quite a niche skill to have, right? Creating shaders, having knowledge of how to build shaders is quite a niche skill. And for that reason, these kind of people are in demand. So if you want to get into shader artists, not just for the love of creating visual effects, this is a really good idea because it's a good way of diversifying your skills outside of games development. For example, the film industry is they have a huge role in computer graphics, right? I mean, computer graphics the other way, sorry. Computer graphics has a massive role in the film industry now, and shader artists are quite literally in demand. For that reason, being a shader artist can be very lucrative. There's quite a lot of shader artists out there who have really quite high paying jobs. So that's another reason to get into shaders. And besides all this, I think the best reason to get into shaders is it's a lot more than just creating what a material looks like. So here on the left, I did this render in Blender the other day, and as you can see, there's a bunch of different surfaces here. This one's kind of reflective. I've got like I don't know what you'd call that, like a checkerboard tile thing, which is quite reflective. This one's kind of transparent, and then you got some up here which are quite shiny. When people think of shaders and people think of materials, this is usually what they think of. They think of the physical kind of properties of 3D objects. So this one looks quite smooth. This one's kind of reflective. And they think that that's all that shaders can do, is just define what a surface looks like in 3D. But the truth is that it's so much more than that, right? I've seen shaders which are just incredibly creative. And to give you an example of that, here's a good example of a really, really interesting shader. It's one of my favorite examples of something that isn't just, you know, creating an interesting looking surface. So you might think, okay, that looks cool, but what's the big deal here? And as you can see on the right, you can kind of see that there's rooms, you know, it looks 3D. But the bit which is crazy about this is these tiles on the right are completely flat. There's no depth, there's no room. This is all done through shaders. So you can create really interesting effects like this and make your buildings in your virtual world or whatever look 3D. You can give them that depth. And that's such an interesting use of shaders, you know, because you're mimicking this 3D room kind of effect. I mean, there's nothing kind of special going on here. It's just an optical illusion almost, you know, it's visual trickery. This is a really good example, and it was created by someone on ArtStation called Trey McNair. if you want to get into shaders and learn about interesting approaches that people have to things like this, ArtStation is a really good resource for that. Here's some other examples. So on the left, we have simulated effervescence. So you can imagine this kind of effect that it almost looks like a fizzy kind of thing, or you've dropped a tablet, like a effervescent tablet into some water. You can imagine this for something like a magic potion or something, but this is done entirely with shaders, right? So you can create really interesting visual effects. You can create things like really hyper realistic snow, like this one in the middle here. And then my favorite example of these three actually is this one on the right. So here we have a ice sheet. So it looks like this character is stood on some kind of sheet of ice. But the interesting thing here is it looks like there's stuff below the ice. I don't know if you can see that. I don't know if you can kind of see underneath this. It looks like there's things below the ice. And there's actually not. This thing here is completely flat. It's very similar to the Windows thing that I showed you. What's going on here is some parallax effects that gives the illusion of depth. But you can create really interesting kind of illusions and stuff with shaders. So such an interesting thing, and I kind of suggest you go on ArtStation and filter by shader. Have a look at some. They're really incredible. So just to give you an idea of what we're going to cover, the first thing we're going to look at is the primer for shading. So we're going to go over some basic computer graphics stuff. We're going to look at what shaders are. Then we're going to very briefly talk about nodes versus code. So how to build shaders with code, how to build shaders with nodes. And then finally, the practical part of this, we're going to use shader graph in Unity. So we're going to build some shaders, just some test ones. They're not going to be great, but hopefully they should give you an idea of how to create better shaders. So let's go on to the primer. So the first thing I want to talk about are 3D meshes, right? So you've probably seen, well, I can almost guarantee you've probably seen a 3D mesh at some point in your life. 3D objects in computer graphics make up a really, really kind of integral part of pretty much any game, any kind of CGI sequence, whatever. So we've got to think about how a computer represents a 3D object. And the way it does this, and this sounds kind of strange, but these 3D meshes are represented like dot-to-dot puzzles. You've probably done these. I used to absolutely love dot-to-dot puzzles when I was a kid. But yeah, dot-to-dot puzzles in 3D, if you can imagine that. And that's pretty much how meshes are represented by a computer. And that sounds kind of strange, right? But I'll get more into it. And obviously that's a bit of an oversimplification. However, at the kind of core of it, that's how meshes work. We have dots, we have connections between those dots, and then we take that and we throw it at the graphics card, and the graphics card shows a 3D object, basically. But you can imagine how 3D meshes are represented by a computer like this. They're just dot-to-dot puzzles in 3D. So when you think about a dot-to-dot puzzle, you normally have this kind of process. You draw the dots, you number the dots, and then you connect them by a number. So here we've got 1, 2. So we draw a line 1 to 2. Then we go to 2 to 3. As you can see, this one here, this dot, is 3 and 7. So when we get to 6, we connect it back up. Right. So we got 1, 2, 3, 4, 5, 6, and then we have this kind of weird shape going here. And then I don't know about you, but when I was quite young, I used to color in these dots. I'd draw the shape and then I'd connect them up. I used to have I remember growing up actually in the early 2000s. I used to have this Nintendo dot-to-dot puzzle book, and I used to get one every year because my mom used to know that I absolutely love dot-to-dot puzzles. And I used to sit there, do them, and then color them in. So this was my kind of process, right? Is you'd have the dots that were in the sheet, you connect them up, and then you'd color in the kind of spaces. Now, if you can imagine that process, but in 3D. So as you can see, these are dots, but they're in 3D. I don't know if you can kind of see that, but this one here is further back. It's kind of hard to show, I guess. But these are numbered just like in 2D. You know, you've got 1, 2, 3. I haven't done it for all of these just because, well, quite frankly, I'm lazy. But all of these are in 3D. Now, the technical term when we talk about 3D meshes, about these dots, they're called vertices. Okay, so as I say here, dots are called vertices. So we don't call these dots in computer graphics, we call them vertices. If we're talking about one of these dots, it's called a vertex. Okay, so here's a bunch of dots in 3D space. We number them up to kind of tell the computer how to connect them together in triangles. Then we connect them up. And these lines, instead of just calling them lines, the technical term for them is edges. So there is an edge between two vertices or a line between two dots. And basically, we connect these up, and as you can see, into little triangles. Okay. And these become the fundamental part of a 3D mesh. And once we've got those vertices and the way they connect together to form these triangles, okay, we can take that and give it to the graphics card along with some instructions of how to actually show how that object should be shown, and we can create a 3D mesh. So we can color this shape in just like we did with the 2D dot to dot puzzle. This process here is called shading, right? So let me go through that again. We've got dots in 3D. These are called vertices. Then we connect them together. We tell the computer how they're connected together to form this 3D mesh. These are called edges. And then finally, once we've got the vertices or the dots and the lines between them or the edges, we can give that to the graphics card along with the set of instructions saying, hey, I want it to look red or something. And the graphics card will just color it in. And that's all graphics card really does, really. It's a bit more complicated than that, obviously. But graphics cards just sit there and just color things in. That's their entire job, right? Is you just give it things and you say, I want you to color this in, and here's how I want you to color it in. Now that how and the instructions behind, like, I want you to color this part maybe red and this part maybe yellow. That's what shading is all about. So you might think, how does the computer know that this triangle here should be lighter than this one here? Why is this one really dark? You know, how does the computer know to do that? And that's where shaders come in, right? This is called shading. Shaders tell the graphics card how to render things. That's all a shader is, right? There are many different types of shaders, which we'll get into. But that's all a shader does, is it just tells the graphics card how to render things on the screen. And what you'll probably see is you'll see something like this. You'll have a shader on the left, whether it's code, whether it's nodes, whatever. And then you pass that to the graphics card along with, a mesh or whatever, or the scene and a bunch of other data. And the graphics card will draw that thing on the screen for you. Now, there are many different types of shaders out there. There's GPU compute shaders, you've got tessellation shaders, you've got geometry shaders, you've even got things like surface shaders, PBR shaders, all different types of shaders. But the two main ones that we're going to look at today, and probably the two most important ones, are Vertex Shaders and Fragment Shaders. So remember, Vertex means one of those dots in 3D, right? So Vertex Shaders are per vertex processing, okay? And I'll go into this in a bit more detail, but basically the shader, the instructions that we give the graphics card to render a particular thing is run on each vertex, okay? Now, really, I mean, vertex shaders, you can do a lot of interesting stuff with them, but really the main purpose of vertex shaders is to just tell the graphics card where the object will be in the virtual world, and how it should look like, whether it's scaled, whether it's rotated. We can alter this process to create some really interesting effects. Again, we'll get into that, but I just want you to know that vertex shaders deal with the vertices, they deal with the dots, right? Fragment shaders, on the other hand, are much more like what I was talking about before. They're all about the appearance. Okay, so vertex shaders is all about where the object is, if it's scaled up, if it's rotated, all this kind of stuff. It's all about the vertices, moving that object, distorting it. It's all about the geometry. Okay, the fragment shader is more about how that object should look, right? So do you want it to look red? Do you want it to look maybe quite shiny? This is what a fragment shader is all about. It's ran per pixel on the output, but this defines what the surface should look like, right? We give the graphics card a set of instructions along with the geometry, and we can tell it that the surface looks a particular way. We can say, oh no, we want it quite shiny, or oh, we want to have some Fresnel effects and stuff in there. So I just wanted to make the point that these are two very different things, but together they allow you to put an object in the world and then color it a specific way. So vertex shaders, like I said, their primary purpose most of the time is to just take a bunch of 3D vertices associated with the 3D model. So all those dots that are associated with the 3D model, and transform them. If you've ever worked in any game engine, if you've done any OpenGL, you've probably heard of transformations, transformation matrices. You've got, the model matrix, the view matrix, the projection matrix, and then you combine these to the model view matrix, the projection matrix, you multiply them together. You've probably heard of this stuff if you've done anything with computer graphics. But that's all Vertex Shader does. It just takes these vertices which are associated with the 3D model, and it transforms them in some way. It might move the object far off into the distance. It might scale it up, scale it down. It might squish it, It could rotate it slightly. As you can see here, here's an example. We have Suzanne, the Blender monkey. And then we apply some kind of scale and rotation using the Vertex Shader, and now it looks, a bit squashed and rotated. The Vertex Shader just tells the GPU how to do this. It tells it about the transformations that should be made to the vertices, their positions, okay? And hopefully that makes sense. And this is how objects are placed into specific places in the world, okay? And using this, we can create some really interesting distortion effects. And here's some examples. So here on the left, we've got the kind of standard Vertex Shader where we just say, just do nothing. I don't want to really distort the mesh at all. Here, what we're doing is pushing vertices in the direction of a normal. Now, I'm not going to get into normals and stuff because it's not really the topic of this talk. But all a normal is really it's called a normal vector. It's just the arrow that points outward from a surface. So if I used to use my water bottle as an example, you could kind of imagine if I've got a pen here, this being the vector. So the normal of this surface is this pen. And then up here, the normal is here. It's just an arrow that points outward from the surface. Okay. I don't know if that's a really good analogy or anything. But that's all a normal vector is. In computer graphics context, of course. But all we're doing here, is we're pushing them in the direction of that normal. So we're bloating the mesh, and we can create interesting effects like this that you could use somewhere in your game. And then finally, we have this effect, but we do it over time, and you can create this kind of rippling effect. And this rippling effect is, you can imagine this as like an underwater effect or something like that. So with a fragment shader, it's a lot different to a vertex shader. So vertex shaders, like I said, are all to do with the geometry. It's all to do with taking those dots, those vertices, and transforming them, squishing them, rotating them, moving them somewhere, right? Fragment shaders are different. Like I said, it's all about kind of painting the surface, right? We have the dots, we have the connections between them, but a fragment shader kind of tells it tells the graphics card what the skin of the object should look like, what the surface should look like. And another term for this is a fragment, what the fragments, the individual triangles should look like. And that's why it's called a fragment shader. So fragment shaders are different in the sense that they run per pixel than per vertex. So vertex shaders, say you've got 100 dots, 100 vertices in your mesh. A vertex shader will run 100 times because there's 100 vertices. Fragment shaders are very different. Because they're done per pixel, we're talking about actual colors on the screen, they're ran per pixel rather than per vertex. And all it does really is, like I've said before, is it just tells the GPU what color a given pixel should be, given, the place it's at right now, the normal, all this kind of stuff. We can use that input data and create some kind of color with it. That's all a fragment shader is it's just literally what the surface should look like. And we use fragment shaders to kind of shade and instruct the GPU as to what the surface should look like. It's very similar to something called a surface shader, which is something we might touch on actually in the shader graph part of this talk. But that is another topic for another day. So to give you an idea of a fragment shader in use, so here's a kind of floating island thing I made in Blender a while back. So if you imagine you looked at this region here specifically on this island, right, and we took that and we blew it up and showed these this grid of 3x3 pixels here. So what we're doing is we're just zooming into a part of this mesh, right? For each pixel, what's happened is we've took the X and Y of that pixel on the screen. That gets passed into the fragment shader kind of conceptually. The fragment shader it runs its code, runs the instructions of like, oh, okay, this pixel is this pixel, and what I need to do is, take the data and blah, 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 do some interesting stuff with it. The fragment shader will spit out a color to put on the screen. Okay, so that's all that's going on here, right? Is for each pixel of this mesh, what's happening is we're taking in the X and Y, we're passing it to the fragment shader, and the fragment shader is spitting out some color to draw onto the screen. So there is actually hopefully that all makes sense. If you have any questions about this, let me know. If it hasn't made sense or anything, feel free to ask me anything. But there is a bigger picture here. So there are things called shader programs. Now, if you can imagine a vertex shader and a fragment shader kind of in tandem, these two together will tell you where an object should be, what its vertices should look like, and also what the surface should look like. The fragment shader tells the graphics card what colors something should be. So these two together are mostly used to render most things, right? Now there is an umbrella term, or not an umbrella term, sorry. If you combine these two, this is called a shader program. Okay, now shader programs can have other types of shaders in there, and there's a lot more nuance to it than just this. But you can imagine a vertex shader and a fragment shader kind of goes into this larger kind of container conceptually called a shader program. Okay, and that shader program is what we pass to the graphics card. So what we do in something like OpenGL or whatever is we can create these shader programs. We can attach these shaders to the program. But you can imagine a shader program is just has one or two slots, and we just put in vertex shader, we've put in a fragment shader, and then they're now bundled up in this kind of package, and we just kind of send the package over to the graphics card, and the graphics card's like, cool, everything's great, I'll compile them for you, and then it knows about those shaders. But I wanted to make the distinction here because that's how this stuff works. Now, shader programs can take input data, right? And this is the reason I was talking about shader programs, is that we can feed input data into these into these shader programs, and it kind of makes sense. I mean, the whole point of shaders is to create visual effects, right? And it wouldn't be pretty good if we had a visual effect that we couldn't tweak. Say you make an interesting, I don't know, shader that makes stuff look like water. It would be a shame if you couldn't change the color of that water. Maybe you want kind of green water for maybe acidic stuff, I don't know. And maybe you want like a kind of greenish blue for the sea. But that's some kind of input data. You would pass the shader a color, right? And that would be the kind of tint of the sea or the water or whatever. And that's the cool thing, is that shader programs, these vertex shaders and fragment shaders kind of bundled into this package, conceptually we can pass input data into these shader programs. So and these are just like variables. So here we have a variable here called model view matrix. Don't worry too much about what that is or its purpose. And it has a type, and this is very similar to any programming language that you've ever used. Any typed programming language, I should say. So something like C# or C++, where variables have types like ints, bools, whatever. This is similar. We've got a variable name called model view matrix. Its type is a 4x4 matrix. We've got something called world time, and its type is a float. So this is just the time or in the game. And then we've got position, and the position is a 3D vector. So that all makes sense. You've got a variable name, you've got a variable type, and this will have a value. What part of this, which might be a bit confusing, is this last part, input type. What's this thing called a uniform? And this thing, it's called again, an input type of uniform. And finally, we've got this thing called an attribute, input type attribute. So what does that mean, right? Well, we're going to get into it here, right? So there are two ways. There's two types of kind of variables that we can pass into shaders. There are uniforms and there's attributes. Okay. Now there's the only kind of difference between these two is the how do I describe this? It's if the data is specifically for a vertex. What I mean by that is, okay, so if you look at this diagram here, we have 3 vertices, okay, 3 dots, and they all have three different numbers here. We've got 25 attached to this vertex, we've got 13 which is attached to this vertex, and we've got 6 which is attached to this vertex. Now attributes are data, right, which could be different for every vertex. So this vertex here has 25. This vertex here has 13. This vertex here has 6. These aren't the same numbers, okay? So a vertex, an attribute, is short for a vertex attribute, okay? And all it means is that the data is attached to a vertex, right? So it might be different for each vertex. This is why they're called vertex attributes, is because they're attributes of the vertex itself, right? So we can kind of say this vertex has this value, this vertex has this value, this vertex has this value. The point is that the numbers here are different for every vertex. These numbers are therefore attributes of the vertex, of the vertices, sorry. And that's where the name comes from. Now, the naming system in computer graphics, I mean, I have some kind of issues with it. It's a bit odd, but you just get used to the kind of jargon. But vertex attributes, that's all these are, really. It's just data that is specifically for a vertex. So things like the position of a vertex will differ greatly between each vertex. One vertex might be kind of here, one vertex might be here. They therefore have different positions. Normals, right? Each vertex might have a different normal. Each face might have a different normal. UVs, things like that. Data which is attached to each vertex, which might be unique or might be different between each vertex, are called vertex attributes. Okay, so that's what attributes are. And I've gone into a lot of detail of what that is. And there's a reason for this, because uniforms, the other type of input into shaders, is the complete opposite. Uniforms are the same value for each vertex. Okay, so here you can see we have 3 vertices. This has the value x, this one has the value x, this one has the value x, and x is equal to 5. So if we change this to 8, all of these 3 vertices would have 8. But the point is that uniforms are the kind of complete opposite of attributes. All uniforms are is the value is kind of, we have a variable, and that variable is passed to all the vertices with the same value, right? You could say that the value is uniform across all vertices, And that's where this name of uniform comes from. So we talk about attributes as being per vertex, okay? And we talk about uniforms as being per mesh, because the uniforms are passed to all the vertices, right? In the shader, in terms of the shader, they're not attached to a specific vertex. They're just attached to the mesh in general. So you can think of this as variables like time, scale, distortion amount. All these variables are going to be the same no matter what vertex we're processing, okay? So I just wanted to make the distinction here that attributes are different per vertex. Okay, so this one has 25, this one has 13, this one has 6. They're all different. Uniforms, however, are the opposite. They're just one variable which are the same across all vertices. They're uniform across all the vertices. So to illustrate this in a bit more detail, here we have a 2D dot to dot. In fact, the very same one that we looked at earlier. So each vertex here has a different number. You could think of these numbers as attributes because each vertex has a different number. This one has 1, this one has 2, this one has 3, this one has 4, this one has 5, and this one has 6, you know? So these numbers here are kind of vertex attributes because they're an attribute of the vertex itself, right? Hopefully that makes sense. Uniforms, however, are things like the size of these dots, you know? So all these vertices, are the same size, you know, they're the same radius. And what that means is if this variable size is different, if it's different, sorry, I'm not explaining that very well. This variable size, if we were to change it from, you know, let's say this is size 6, if we change that to 8, all of these points would at the same time grow. But what I'm trying to say here is that the size of these vertices is dictated by a uniform called size, and it's shared across all the vertices. So hopefully that's given you a kind of whistle-stop tour of some computer graphics stuff, why we use shaders, and some interesting things about, you know, passing stuff into shaders and so forth. There's two main ways of creating shaders. There's graphical ways of using nodes, and then there's a kind of, well, more kind of imperative way of using code. So code, we literally type in code like we would with any programming language. You know, this here is a shading language called GLSL. So the instructions that we give to the shader, to the graphics card, sorry, the instructions for that shader are represented by text. You know, here we're saying there is a vertex attribute. I mean, this syntax is a bit strange, but we're saying that there's a vertex attribute here called apos, which is a vec3. And here we have an out variable of vertex color. We're saying set the position to whatever, set the color to whatever. So don't worry if you don't understand this, but the point I'm trying to make is that shaders can be, you can represent them through code as well as nodes as well. And this is just one way of representing instructions to pass to a graphics card. Another way is to use nodes. So instead of, you know, typing in text, we can actually use a process very similar to a kind of flowchart. You know, here we've got red and we've got blue, and we can put these into some kind of node called mix. Mix will just kind of mix the two colors together, and then we can set the output pixel, the output color to that mixed value. So we've got red and blue going into this, and then the output from this mix thing we can put into the final color. Now, I don't know about you, but this thing here makes an awful lot more sense than this. And both have their pros and both have their cons, but yeah, they're two different ways of kind of informing the graphics card of what you want to actually do in the shader. This approach here, nodes, is usually called low code. So I might switch terms. If you hear me say low code, this is what I mean. I mean nodes. So this is what we're going to look at today, because that's how, well, that you can create shaders within code with Unity. But it seems like the future is going towards this node-based system, these node-based graphs. So node-based graphs are a very interesting way of describing any kind of process, any kind of system, right? So as an example, just to get you used to this, let's imagine making a cake, right? So the classic imperative way of making a cake is a list of instructions, right? And you know, also here, by the way, I'm not sure if this is a valid recipe for making a cake. As you can probably tell, I don't make a lot of cakes, but if you ignore that, this is just to give you an idea of what I mean between imperative and node-based. So here we just have a list of instructions for making a cake. You know, it says get the eggs, get the butter, get the baking powder, basically get all the ingredients, mix them together, you know, into some kind of cake mix, right? Put it in the tin, and then bake the tin for, I don't know, 30 minutes at a particular temperature, and then finally, you know, cool them off, serve, right? So this is a recipe almost. It's not a very good recipe because it doesn't tell you how much eggs to have or how much butter to put in the mixing bowl. But it is giving you instructions, an imperative procedural list of instructions that you could follow from step one to the end and eventually have a cake, right? This is usually how we represent processes, whether it's code, whether it's things like recipes. This is an imperative way of making a cake. The other way is to make a cake using some kind of node-based system, right? So here it's the same process. We're just looking at it in terms of nodes, right? So we have the ingredients: butter, egg, flour, and sugar, and these all go into this thing called cake mix, right? And then we can put the cake mix into the oven or put into the process called bake, and then this variable of 30 minutes goes into the bake thing as well. So we're baking the cake mix for 30 minutes. And you can kind of see what I mean. You know, we have the ingredients, these all go into this thing called cake mix, and then all we're doing is we're just passing that into the, you know, oven, the bake process, whatever, and then we get our cake. So it's the same process, we've just represented it in a different way. And that's the difference between writing shaders with code and writing shaders with node-based stuff. So on that note, I'm going to just go through some Unity stuff, and hopefully we'll go into a bit more detail on how to use these shader graphs. Right, so let me fire up Unity. It might take some time, and hopefully, you know, this demo is going to be fairly brief. So one thing I want to note: if you want to create a project where you can use shader graphs, what you want to do is go to the new project and make sure you've either got the high definition render pipeline checked or the universal render pipeline checked. If you instead go for 3D or 2D even, what's going to happen is you're not going to have access to the shader graph system. So make sure you've clicked universal render pipeline or high definition render pipeline. I've already made a project, so I'm just going to open up this project for you. So we'll just wait for Unity to open, and I might take a sip of water. Right. So what I'll do is, well, I'll put the inspector somewhere here. Yeah, let's leave it there. Yeah, we all have everything. So we've got a camera, we've got directional light. There are some example assets here. Let's I might actually just make a new scene because it's a bit easier. So let's just create a scene. Let's not save that. So now we have a kind of blank scene. I'm just going to add a sphere to the scene so we can actually see something. So let me just make this sphere a bit bigger, and let me just align this. So now we have a sphere and our camera is looking at it. So the first thing to do is I'm going to make a new folder. I'm going to call it something like shaders. Okay, and in here I'm going to create a new material, right? And let's call this, I don't know, sphere material. I'm just creating a sphere material. I'm going to drag it onto this sphere here. So now we have a sphere with this material, and as you can see, you know, we can change properties of this. You can make this red, you can make it black, whatever. But how do we actually start building our own shaders? Well, all you do is you go into your project here and you right click, you go to create, and here we have something called shader. So what we're going to do is go here. Now there are a bunch of ones here, but you want one. You want the option here that says Universal Render Pipeline. We've got lit shader graphs. We've got unlit ones. I'm going to go for lit. So I'm going to create a new shader, and I might just call it like a test shader. So that's how you create a shader. Okay, it's very easy. Like I said, you just right click, go to create, shader, Universal Render Pipeline, and then you've got your options here. If you don't know which one to choose, I would say go with the lit shader graph here. So how do we actually get the shader onto this object, so to speak? Well, it's fairly easy. As you can see, when I click on a material here in the project, you can see that here it's got a little shader thing. Now you can go here and go all the way down to, well, Universal Render Pipeline. I think it might be in here. No, I think it's, yeah, shader graphs. Here we go. And we've got our test shader here. So what this is doing is it's saying that we're kind of attaching the shader to this object. So each material in Unity has a shader, and this is how we specify what shader to use to render a particular object. So I'm just going to click on this, and let's go to, I'll keep doing this, shader graphs, and I'm going to click on our test shader. Okay, so now this object is using our shader that we've just made. So that's all you have to do, right, is create a new material, change the shader of it to the one that you've just created, and now we have this object which is using our test shader. So the next question is how do we actually edit this shader? So it's very easy. We just double click it, okay, and you'll see this this window pop up. This is shader graph, or the shader graph editor. I'm going to try pop it out so we can kind of see it in full screen. So let me just resize this. There we go. So, and this is our node-based system, right? So we can use the middle mouse button to move around like this. We can use the right mouse button to click and create nodes, and we can left click on nodes like this to move them around. All I'm doing is left clicking and dragging here. But as you can see, we've got a vertex bit and we've got a fragment bit. Okay. And this is pretty much what we were talking about, right? You can we have attributes of the fragment shader, like the color that we want to put into if we want a particular fragment to be a certain color. So for example, we can change this to red, and then if I go back to the if I save this asset up here in the top left and I move that out of the way, as you can see, it's red. If you want to put inputs to your shader, then this what this little window here is on the right. So as I said, we've got uniforms and we've got attributes. In Unity, I think you can only create uniforms. Yeah, you can do it through code. You can change attributes and stuff, but we can create a input, right? A uniform. Let's make one that's a color, for example. Okay, and let's call this like I don't know, surface color. Okay, so now we have a variable called surface color, right? We can click and drag this into this region here, and now we have a surface color, but we don't actually have this hooked up to anything, so to speak. So what we can do, this input that we're kind of saying, I don't know what the value is, but whatever somebody specifies, we can connect this to one of these things. So we can control many different things in the fragment shader. We can control the base color, which is just the color you see here. We can control the normal of the surface, right? The normal vector, like I was talking about. We can control how metallic the surface is, how smooth it is. So as I turn this up and down, as you can see in the bottom right, let me try make this a little bit bigger for you. So as you can see, like as I change this value up and down, we're making it either really shiny or really, well, kind of dull. And that's what we can do. We can feed things in. We can kind of make a node here and kind of connect it up to this and say, this is how smooth I want it to be. We've got the emission color, we've got ambient occlusion. And how we connect nodes together is, as you can see, they've got these kind of dots. So all you have to do is click and drag on one dot and drop it on the other. So now this surface color is going into the base color of this of this fragment shader. So if I go back to my inspector, right, if I click on the sphere material, as you can see, there's an input here now called surface color. And what we can do is we can click and we can change this, and we can change properties of this in the inspector itself, right? So that's a really kind of interesting thing. That's how you create uniforms in Shader Graph. But I'm not going to get into too much detail on Vertex and Fragment Shaders, but I just wanted to kind of introduce you to node-based systems, introduce you to shaders, and then, you know, hopefully show you a little bit of Unity here and how to connect some stuff up. So we could, for example, do some really interesting things. You know, we can create a node here, or, you know, we could have a texture, you know, a texture 2D. We could call this like a texture. We could have a texture here. We could sample this using sampler, right? And then we could take this color and pipe it into the fragment shader. So now what we've got is, hopefully we've got a texture. You know, if I click on this, now we've got a texture displaying on the object itself. So all that's happening here, okay, is we've got a texture here that we can specify in the inspector. We can we sample that, saying what's the color at this particular point. We shove it into the color itself, and now we have a texture texture showing on the object itself. But we can interrupt this process. You know, we can do things like, well, what if we did something like make a float? We'll call this like I don't know, opacity. And bear with me. Let's put the opacity there, and then let's do mix. I think it's mix. Is it lerp? Lerp, yeah, that's the one. So lerp, we can take the opacity, we can shove it in here. We can take the output of this texture into this lerp. Then we can do things like take the surface color, whack it in here, so we're lerping between those two, and then shove it into the base output. So now what we should have is a we can kind of control whether or not this is you know, what's that color, like a red color, you know, if it's red, or whether it's a texture using this one value. You can imagine this kind of effect for, you know, if an enemy gets hit, you could go, oh, make it red, and then go back to normal or something. And I probably went through this fairly quickly, so don't worry too much if you don't understand what's going on here. It's the point of this is not to show you how to make effects. It's rather to get you used to this environment of nodes and connections and all this kind of stuff. So what's going on here really is we're sampling a texture, and lerp, all it does is it fades one thing in and fades another out. It like interpolates between the two. So here we've got the red color, and here we've got the texture, and we're just saying use this variable as the percentage between those two, and then finally the output, just whack it into the base color. If that doesn't make much sense, don't worry about it. The point of this, like I said, is to kind of give you a bit of shader primer, and then go into node-based systems, and then just show you how you can actually do this stuff in Unity. If you're looking at more guidance on how to create specific effects, how to use this in more detail, like I said, I have done a talk on this previously, and I think it should be on this YouTube channel somewhere. Just search shader, where I go into a bit more detail of how to actually use these things and how to use the interface. Another good idea is to have a look on Unity's official tutorials. Unity has an amazing resource for tutorials out there, specifically on shaders. So I would say have a look at those. Have a look at the previous talk I've already done. Hopefully that all made sense. I'm just going to go back to this presentation. And on that note, I suppose I think I'll end it there. If you've, like I said, if you've found this interesting or whatever, like I said, the best idea is to kind of have a look at some of the other talks in this enhancement week. And yeah, like I said, have a look at the previous talk I did on shaders, because that seems like the next logical step. This hopefully gave you a very brief introduction into 3D graphics and shaders. Have a look at that other talk. It should give you a bit more detail on how to use shader graph. But yeah, I think that's it from me. If nobody else has any questions, yeah, I think I'll end it there. So thanks for listening, and yeah, cheers.